In this lecture, we learn how to use counting techniques in solving probability problems. We learned in the previous section how to use combinations, how to use permutations, factorial, and some other techniques to find number of ways of performing some experiment. Before we start discussing some problems, I want to remind you of two things. The first thing is what we call uniform sample space. By this we mean that the outcomes of an experiment are equally likely. And the second thing, the basic probability formula or basic probability rule, probability of an event to occur is number of outcomes of that event over number of outcomes of the sample space. Now let's start with the first problem. Now here in this section we focus on number and problems with a large number of outcomes in the sample space. So in this example, first example, we toss a coin 6 times. Toss a coin 6 times, and we want to know what is the probability that a coin will land heads exactly 3 times. Okay, now first we define the event. The event E is getting head 3 times. And after that we want to find the probability. Here it's not easy to determine the sample space because, or the all of outcomes of the sample space, because the coin was tossed 6 times. Now applying the probability rule, probability of an event is number of outcomes of the event over number of outcomes of the sample space. Now when we toss a coin 6 times, and the 6 times we get 2 outcomes in each stage of this experiment. We get only 2 outcomes, head or tail. So in the first stage we get 2 outcomes, in the second we get 2 outcomes, up to the sixth stage we get 2 outcomes. That means we have 2 to the 6th outcomes. So number of outcomes of the sample space is 2 to the power 6. Now what is number of outcomes of the event? Getting 3 heads. Now getting 3 heads, here order doesn't matter, so we can use combinations. So from 6 tosses we want to get heads on 3 of them. So that means by applying the combination formula, we have 6 factorial over 6 minus 3 factorial times 3 factorial over 2 to the power 6. Now we simplify. We have 6 factorial over 3 factorial times 3 factorial times the reciprocal of the denominator, 1 over 2 to the power 6, which is 1 over 64. And then we simplify. 6 factorial is 6 times 5 times 4 times 3 factorial over 3 factorial times 3 factorial times 64. We can cancel 3 factorial and simplify, and 6 is actually 3 factorial. So this gives 5 times 4 over, and we can simplify 64 over 4 is 16. So we have 5 over 16, which is equal to 0.3125, or you can use the calculator to find this. And it's very important to know how to use the calculator to find combinations. Sometimes you see this symbol to denote computation, and this is for permutation. So it's very important to be familiar with these, with how to use calculator to find combinations, permutations, and factorial. Now for B, at most 3 times. We want to get head at most 3 times. What does that mean? That means either 0 time we get head, or 1 time, or 2 times we get 2 heads, or 3 heads. At most 3 heads means these cases. Now when you take probability of getting 0 head, or means plus probability of 1 head plus probability of 2 heads plus probability of 3 heads. Now probability of getting 0 head, that means from 6 tosses we get 0 heads. And I used another notation for the combination. Combination can be written as C60 or 60 this way. Those are the same, just notation. So we can use either one is okay. So let me use C, the letter C. So this is C60, this is C61, this is C62, and this is C63. Now we divide by the number of elements of this outcomes of the sample space, which is 2 to the power 6. Now computing this, we get 42 over 64, and that's can be approximated as 0.6563. This is the probability, and as you notice here, the probability is less than 1 and greater than or equal to 0. The probability cannot exceed 1. Now the part C, we want to see what is the probability that we get a head on the first and the last toss. So the first and last toss, that means this is first, the first toss we only have one option, or one choice. So from 1 head we choose 1 head, or if we want to write it as C, from 1 head we choose 1 head, and on the last one we choose 1 head from the 1 head. So from 1 head we choose 1 head in this stage. And the other ones, we have 2 options from 2 outcomes. Here from 1 outcome, which is head, we just choose head. So that means this is specified and this is specified. We don't have choice. We just choose head. But for the second one, for example, the second toss, we have 2 outcomes, either head or tail. So we have 2 C21, we choose 1 out of 2, and for the second one, the third one, the fourth one, we have 2 choices. We can choose any one of them. But for the first one and the last one, we don't have a choice. We have one option. We just want our 1 outcome. It's specified, 1 head, and we choose that head. So or you can use the other notation. You can write it this way: 1 1, from 2 you get 1, from 2 you get 1, 2 outcomes you choose 1, 2 outcomes you choose 1, and from 1 head you get 1 head. So those are specified, all over 2 to the power 6. So this is 1 times 2 times 2 times 2 times 2 times 1, all over 2 to the power 6, and this is 2 to the power 4 over 2 to the power 6, which is 1 over 2 squared, 1/4 this is 0.25. So here we only have one specific outcome, but here we can have either head or tail. That means we have two outcomes, or two outcomes. We choose one of them. Now the second problem is that we have two cards. We want to choose or select two cards randomly without replacement from a well shuffled deck of 52 playing cards. The question is, what is the probability that they are both aces? So they are both aces. That means we are choosing two cards, both are aces. Let's define first the event. The event is this: E getting two aces, and the probability here is number of outcomes of this event over number of outcomes of the sample space. Number of elements of the sample space is, now from 52 cards we choose 2. That's the number of outcomes of the sample space. But getting 2 aces, we only have 4 aces. So from 4 we choose 2. And using a calculator we get 0.0045. Now for part B, neither of them is an ace. What does that mean? So this is the event F. Let's call it F. Probability of F is number of outcomes of F over number of outcomes of the sample space. Sample space is, we choose 2 out of 52 outcomes, or 52 cards. And for number of elements or outcomes of the experiment of the event is neither of these 2 selected cards is an ace. That means from 48, because aces are 4, so we exclude them from this set of 52 cards, so we get 48 cards. From 48 cards we choose 2, and then we can use the calculator to get 0.8507. And as I mentioned, this is the same as, we can use this notation actually. From 52 we choose 2. So if you want to use calculator, it's better to remember this notation rather than this notation. Okay, the third problem: a box contains 100 blank DVDs, of which 10 are known to be defective. If 6 DVDs are selected at random, what is the probability that 2 of them are defective? So here we have the event that 2 DVDs are defective. So probability of this event is number of outcomes of this event over number of outcomes of the sample space. For the sample space, it's very easy to determine the sample space. From 100 DVDs, we choose 6. And for number of outcomes of the event, from 10 defective, we have 2. We choose 2 DVDs, and the rest will be chosen from the 90 DVDs, 90 non-defective DVDs. And here I use the word and means multiplication. So from the 10 defective DVDs, we chose 2, and multiplication from the rest of the non-defective, from the non-defective or the rest of the DVDs, this is 90. We choose the rest of the DVDs, 4 DVDs. And as you can see, if the sum of the top numbers is 100, the same as the top in the denominator, and the sum of the below numbers 2 and 4 is the same as the below or chosen number 6. So using a calculator we get 0.096. This is the probability of getting 2 defective DVDs. Now if we want to find the probability that at least one of them is defective, at least one, that means probability of getting 1 defective, or means plus probability of 2 defective, or probability of 3 defective, or probability of 4 defective, or 5 defective, or 6 defective. But instead of finding all these probabilities, it's better to apply the complement rule. The complement rule says that in order to find this, this is equivalent to 1, the whole probability, it's 1, minus probability of getting 0 defective. This is complement of this, and we just find the probability of getting 0 defective. This is 1 minus, now 0 defective, that means from 10 defective we choose 0, and from the 90 non-defective DVDs we choose the 6, and from 100 for the sample space we choose 6. Now using calculator we get 0.478. The probability is approximately this. Now this example, a group of 5 people is selected at random. What is the probability that at least 2 of them have the same birthday? We assume that a person is equally likely to be born on any day of the week. So for this problem we have the event that is that at least 2 of them have the same birthday. This is the event E. So probability of E is number of outcomes of E over number of outcomes of the sample space. Now here we have number of outcomes of E is we have 2. Probability of having, we are saying that at least 2 of them have same birthday. We have, since we have at least, so that means we start from 2. So 2 have the same, or 3 have the same, or 4 have the same birthday, or 5 have the same birthday. And as in the above problem or the previous problem, instead of finding all these probabilities, we can find 1 minus probability of none of them have the same birthday. So this is 1 minus probability of none of them have the same birthday. That's permutation of 365. We choose 5 of them. So that means 2 have, we can write it this way, 1 minus none of them, that means 365 for the first one, for the second 364, and third 363, and then 362, and then 361 days, all over 365 to the power 5. This is the number of outcomes of the sample space. So each one person have 365 days. So 365 times 365 6 times, that's 365 to the power 6. But here none of them have the same day, so we have birthday, we use the first one has 365, the second one has 364 because one of them is already chosen or selected, the third one has 363, the fourth one 362, and the fifth one has 361. This is a probability of having none of them have the same birthday. Now using a calculator we get 0.027.